Welcome back, Structures of Math students. This is Mr. Marquetta, and today we're going to explore chapters 11.1 and 11.2. We're still in our unit 4, which is about ratio and proportion and thinking about multiplication and division in different ways for the kids. And today we're going to explore factors, multiples, and primes and composites, and we're also going to talk about prime factorization. First, let's put aside some important definitions and get over these and be comfortable with these right now, because we're going to keep on coming back with these words prime and composite. First, what is a prime number? A prime number is a whole number that has exactly two different whole number factors. That's one way to say it. Another way to say it is a prime number is a whole number that has only itself and one as its factors. There's different ways to say different things in different textbooks in different states and different countries say things in different ways. For me, a prime number is a number that only can be divided by one and itself. That's how I was taught when I was a child. This is another way to say that. Say it however you like. Say it in many different ways when you're teaching so that your kids can get it from all different angles that way. Also, we have a composite number is a whole number greater than one and has more than two factors. Okay. So actually looking at these definitions in your textbook, there is a little bit of a flaw. I don't know if you could see it or not, but when it comes to prime and composite numbers, the number 1 is neither prime nor composite. However, your first definition here says, well, the prime number is a whole number that has exactly two different whole number factors. Well, I guess that follows for 1, because 1 only has one factor itself. So, and itself is 1. So I guess you could really go into a logical spin with that if you really want. Let's make it easy on the kids. The prime numbers are the numbers that are only divisible by 1 in themselves, and a composite number is a number that's divisible by itself and 1 and at least one other thing. What you're looking at here is something we call the sieve of Eratosthenes. And the sieve of Eratosthenes is a methodology to figure out what all the prime numbers are up until a certain number. In this scenario, you're looking at an investigation of all prime numbers up until the number 126. So from 1 to 126, we can figure out what all the prime numbers are if we follow Eratosthenes' algorithm, and I'm going to explain that with you right now. Let's talk for a minute about these words. Who is Eratosthenes? He's an important philosopher that contributed to mathematics in many ways. Specifically, today we're studying this particular thing that he contributed. What is a sieve? That word S-I-E-V is synonymous with a strainer, that when you strain macaroni, or you might have heard that word if you ever studied the sport of fencing, where people are fencing and they have swords where they're fencing with each other, and they put a mask on that looks like a sieve. Also, some coffee pots have a sieve for a basket, meaning that you don't have to put a paper in it. A sieve is basically a very thin screen that you can only let certain things will pass through it. And Eratosthenes' sieve is just that. It's something of a screen or a filter that will kind of remove all of the composite numbers from this list, leaving only the prime numbers. And that's what we mean by Eratosthenes' sieve, is taking a bunch of numbers and literally filtering them such that only prime numbers are left. So the first step of Eratosthenes' sieve, will always be exactly the same step. It will be cross out the 1, and that's because 1 is always going to be eliminated when you're considering what numbers are prime. 1 is neither prime nor composite, so 1 is out of the picture, so we cross it out. The next number after 1 that we witness there is the number 2. We're going to circle it, and the reason why we circle it is because it's the first number after the last thing that we've crossed out, which was 1. So we circle the 2, then we go through the entire sieve and circle all of the 2's, until you're done and you have all of the multiples of 2 circled. So you'll circle 2, 4, 6, 8, 10, etc. In fact, you might want to get clever and just circle the entire second column, the entire fourth column, and the entire sixth column there, because those are all numbers that are multiples of 2. And then the next thing you'll do is look at the next number that's available. So you had 1 crossed out, you have 2 being circled, and the next thing that's not being written on is the 3. So circle the 3. Now go and circle all of the powers of 3. Eratosthenes' sieve can sometimes be written as a list of numbers that's a little bit easier to use. For example, 6 columns here make it pretty clear and evident that it's the 3rd column and the 6th column that represent all the multiples of 3. So you could just go ahead and circle that entire 3rd column there. 3, 5, 15, 3, 9, 15, 21, etc. Just circle the whole column, because those all are multiples of 3, as are everything in the last column there at 6, 12, 18. Further, because of your background in arithmetic and mathematics, you should know that there are no other multiples of 3 because of that. Okay, so carrying on, 4 has been eliminated because it was circled, and now 5. So for the most part, you keep on going with this until you've exhausted all of the numbers. And what I'd like to do with you now is do an Eratosthenes sieve for only the first 20 numbers so that you can see the general motion of how it works. And I'm going to do it in this motion as well, where we have them written in this particular style. And you'll see using the pencil how you work through the numbers and find the final solution of what the list of prime numbers out of that list was. So let's take a look at the camera, my friends, now, and I'm going to just take a minute and try to jot down all of these numbers. And while I'm doing that, I recommend that you try to do that as well. Let's change our camera. Okay, so here's my list of numbers. Now, if it makes you feel more comfortable, you could put them in a grid, you could put them in boxes, or you could draw lines if you want or whatever. But you know, the way I'm looking at it is I could tell that I'm going in order. I'm using 6 columns because with Eratosthenes sieve, if you use 6 columns, you're a little bit better off. Let's go through that motion I just described. This time instead using our using a pen. Okay, so for this one, we'll start by thinking, okay, one is prime. One is neither prime nor composite, so I'm going to eliminate that one. Okay, I'm going to stop here so that you guys can see what I'm writing. 1 is not prime, but 2 is prime. So if you think 2 is prime, then these are not. You should X them out. I think it's a little bit better. And I'm pretty sure that's what the directions say to do for Eratosthenes sieve that way. Cross them out instead of circle them. The next one is 3. So any multiples of 3 get crossed out, which is this one and this one and this one. The next number is 5. Any multiples of 5? I don't see. 7. So we're going to encourage you guys, please instead use the circle. Do it this way instead. I think the last way I showed you I was misleading. I'm sorry. When I first looked at it, I remembered it wrong. This is the best way to do it. But even so, looking at this example that I wrote, which has got all kinds of circles and stuff all over it, I, at least when I was doing it, realized that I was not in the right position because I was doing things like circling prime numbers and composite numbers at the same time. There's no other X's except this one and this. So, you know, noticing, wait a minute, you got 4 there. You also have these. This is no good. These are all not prime, you know. So I think I kind of went off in the wrong direction with it the first time I did it. Instead, you should do it this way, where you start by crossing out the 1, and then you circle the next thing. And then after you circle the next thing, then you cross out all the multiples of this. So cross out 4, 6, 8, etc. You might see that you could cross out the whole thing is what I was trying to do before, like so. Right? And then the next number is 3, and you carry on. So Eratosthenes sieve is really not that hard. It's just a process that you kind of have to see, and you can do it in a couple of different ways. I would recommend this way more so. The first way I did it might not have been very practical, but doing it that way at least kind of gave you a little bit of a background of how it works. And I could see you guys in the future looking this up and trying to work through the sieve of Eratosthenes with your students, and maybe kind of seeing different ways to do it. You might want to do other things with this, like use coloring or use markers or something to eliminate the numbers. You could use blocks that have numbers on them and take the blocks away, things like that. You know, there's all kinds of fun ways to use the sieve of Eratosthenes. But the point of the sieve of Eratosthenes is that in order to figure out what numbers are prime, you really do have to investigate each and every single number. You have to ask for each and every one number, is this prime or composite? Is this prime or composite? Is this prime or composite? And when you do that, you know, it's a little bit of a test and it can get exhausting. The sieve of Eratosthenes employs the idea of knowing the times tables as a quick getaway for trying to remove these numbers that are composite in the list. And it also gives a little enrichment on getting students to be comfortable with their times tables and memorizing those times tables. Okay, the next important thing we have here is some introductory definitions, and there were a couple of questions in WebAssign that were very misleading that I removed from your chapter 11 practice. You'll see here, we say if n equals p, then m and n are called factors of p, and p is called a multiple of m. Now, we've seen this already in our last lesson where we were discussing factors and multiples. We saw that exact situation, and we were discussing the division model and the partitive view and the quotative view and all those other things. We saw this very situation where we were determining that p is the product, m and n are factors. You could argue that p is a multiple of n and all those other things, okay? We also believe that if mn equals p, and m is not 0, then p is called a divisor of p. And excuse me, m is called a divisor of p. And we say that p is divisible by m. So these are words that you can use, and where they say m is not 0, don't really focus too much on that. Just realize that, you know, if it is 0, then that doesn't work. And if it's 0, that's a special specific case anyway. So don't really focus your attention too much on that. Don't let that throw you off too much. And then last, we have recall also that p is the product of m and n, and the word product is there. So we have some important terminology here: factors, multiples, divisor, divisible, and product. Okay, so now we're going to look at activity number 2, which is our vocabulary, and we're going to try to use sentences and use words and sentences to demonstrate that we are comfortable with and familiar with the words and how they are supposed to be used and what their definitions are. Let's use the numbers 6, 8, and 48 in sentences that involve factor, divisor, product, and multiple. Use rectangular arrays, use equations, use words, and describe the relationship between 6, 8, and 48. So for something like this, I'm going to go through this vocabulary activity here because this is not required for your next exam. And I'd like this for you to see how this works out and how this plays out, okay? We're going to use the numbers 6 and 8 and 48. And the general idea that I'm familiar with here that I'm going to keep on returning to is the concept that 6 times 48, that 6 times 8 makes 48. All right, so let's use sentences that involve factor. 6 is a factor of 48. 8 is a factor of 48. Let's use sentences that use the word divisor. 8 is a divisor of 48. 6 is a divisor of 48. Product. 48 is the product of 6 and 8. Multiple. 48 is a multiple of 6. 48 is a multiple of 8. Now use rectangular arrays. Okay, we could do that. Right? And so on. Okay, so I use X's. You could use circles if you want. You could use dots if you want. You could use lines if you want. And right? Okay, so any way you do it, here's what we mean by the rectangular array. You draw something that represents the idea of 6 times 8. That's your rectangular array. Write an equation. Here's an equation right here for you. Write it in words to describe the relationship. 6 times 8. So in other words, you need to be able to do all these things. Write it in words, write it with an array, write it with an equation, use sentences using the words factor, divisor, product, multiple. So you have to really demonstrate that you really get it. All of those words, how to use them, and these different things that we've discussed. For part 2, it says use these vocabulary words to describe the variables in m, n equals p. So once again, you could go through the same motions. We're saying m and n are factors of p. M and n also represent divisors of p. You could say p is the product of m and n. You could say p is a multiple of m. P is a multiple of n. And then you could also, of course, draw those rectangular arrays, but you know, you have a number here, 6. You'd have to kind of use dots to draw that, but we're not going to ask you to draw that anyway. For part 3, it says if m is a factor of n, is n a multiple of m? If p is a multiple of q, is q a factor of p? The answer for part 3 is yes all around, and let's use an example of that to make it very clear. For example, if m is a factor of n, it's like saying that 8 is a factor of 48. If 8 is a factor of 48, is it true therefore that 48 is a multiple of 8? Yes. The point we're trying to make is that if you use a concrete example for questions like this, it becomes clear that the answer is yes or no. Because if 8 is a factor of 48, 48 is a multiple of 8, you could do it with any pair of numbers that have a factor multiple relationship. If 9 is a factor of 90, then 90 is a multiple of 9. Yes, that makes sense too. So it doesn't hurt to come up with some alternative examples and to do that as well. Notice that for Q and P, it's the same scenario, except they're using Q as M and rather what P is. Yeah, you're using Q as N, and it's the same question, but with different letters. Just take a close look there and you'll see what I mean. So whether it's P and Q or N and M, it's still the same situation. For part 4, it says if M equals 2N, what can you say about M? And this is something either you know it or you don't. In the very specific case that M and N are both integers, meaning that they're both whole numbers or 0 or 1 or negative, but not fractional and not decimal parts. If it is the case that one of them is twice as large as the other, you could say that this number is an even number. And it's even because it is a multiple of 2, and all multiples of 2 are even numbers. All other numbers are odd numbers, and that does play a role a little tiny bit when we're talking about the WebAssign. I'm going to show you a special specific case of WebAssign, and we'll do it together, where they experiment with even and odd numbers. And since we didn't talk that much about it in the chapter, I'm going to make sure that we kind of discuss that in class together. All right? So what does it mean when you see 2n? You can assume that even is part of the story. Okay. Now, let's talk about the number written as a product of prime numbers. That's what we call prime factorization. And we did explore prime factorization a little bit when we were talking about how to find the least common multiple earlier in October. Prime factorization is a way to rewrite a number such that you're looking at it at the same quantity, but being expressed, instead of being expressed as just the number that you're familiar with, it's expressed as a bunch of smaller prime numbers all multiplied together. And when there are prime numbers that are repeated, we use exponents to show that. So the fact that every whole number greater than 1 is either a prime or can be expressed as the product of primes is called the unique factorization theorem, also known as the fundamental theorem of arithmetic. So let's talk about these ideas for a minute. First, when we say a product of prime numbers, it's prime factorization. We're trying to write out a number such that it's a product of a bunch of smaller numbers, like I said earlier. When it comes to the fundamental theorem of arithmetic, there are 3 fundamental theorems, and the fundamental theorem of arithmetic is the one we're focusing on today. There's also a fundamental theorem of algebra. The fundamental theorem of algebra says that any equation of degree n has exactly n solutions. There's also the fundamental theorem of calculus. The fundamental theorem of calculus looks like this. And it's basically relating the idea of area and differentiation versus integration. And there's a long story about why that's the fundamental theorem of calculus. The good news is you don't need to know this or understand this for this point of your instruction, but there are 3 fundamental theorems of multiplication: the fundamental theorem of calculus, rather in mathematics, the fundamental theorem of calculus, the fundamental theorem of algebra, which says that an equation of degree n has n solutions, and then there's the fundamental theorem of arithmetic, which says that every whole number greater than 1 is either prime or can be written as a product of primes. That's the fundamental theorem of arithmetic. And as you can imagine, because of the way it's been named, it's a pretty important theorem, and it's used widely in a lot of different applications. So it's important we're familiar with it. And when someone says fundamental theorem of arithmetic, you should know what that is, especially if you're teaching lower grades. You should be familiar with it. It's prime factorization. Okay, so what I'm going to ask you guys to do is we'll take a short break now, and during this break, I'm going to ask you to focus on activity 7, which is numbers 1 and 2 here. I've also included all of the answers here for you. I'm going to ask you to please make sure that you're familiar with this material, as when we return, I'll be going over how to get these answers and where they came from. In the interim, I'm going to ask you to also please make sure that you go and check your exam and go and check that your grade is fair and accurate. And if it's not, please send me a very friendly and please be kind to me. I'm trying. I've got a lot of students and I make mistakes. I'm only human. If you see a little mistake, please have patience with me and just let me know as nicely as you can. I'll go and fix it real quick for you, and it'll be over before 9:15 today. I'd really like to have all of your exam grades all finalized by the end of our class today. So right now, my friends, it's 8:34. It's a 15-minute break. I'm going to ask you to please return at 8:49 a.m. And at that point, we'll carry on with primes and composites and with even and odd numbers, and we'll look at the answer to this. So between now and 8:49, I'm asking you to please work on this activity and check your exam. Thanks, guys. We'll see you in 15 minutes.
Mr. Marquetta, I have a question.
Hi, Amelia. Hold your question for just a minute, okay?
Okay.
Okay, so carrying on with this chapter 11 lesson, we're going to start after our break with talking briefly about the prime factorization of 200. And the reason why we're going to do that is because there was an error on our exam. That question, find the prime factorization of 200, which was on exam 3, had a faulty answer. There were 4 answers, none of them were correct. The correct answer we're going to find out right now. And between now and our next class, I will be going back to your exam and making sure everyone is awarded the 4 points for this question. So if you accidentally got this question right, which is impossible because all the multiple choices were incorrect, then you already got the points and you won't see a change in your grade. But if you got it marked wrong, then I will go back and give you the 4 points. We also discussed in our break that there is an open-ended question that has to do with filling out a proportional reasoning table, that different students might have different numbers in there. Remember that you must include given in the first row, and if that's not there, that is marked wrong, but the other discussions and connections in the table may be different than the given answer, so we're going to make adjustments for that as well. So I'd like to start our return to class right now by going over this one question from your exam, which is in our lesson today about prime factorization anyway, and then, when you guys go and look at your exams on Thursday, we'll have another conversation in class about finalizing the exam, okay? All right, so if we're going to do the prime factorization of 200, we write the number 200 and we start dividing it by things. It might be practical to start with the lowest prime number we know, which is 2. And we do it again. And we do it again. And we do it just one more time. 25 becomes 5 times 5. So here are all your factors. Your solution should be this, right? And this answer was not there. Unfortunately, I had typed the number 3 there instead of 5. So eLearning Blackboard thinks that the correct answer is this, when it's not. That's not correct. If you chose this, it marked you correct. If you did not, it marked you incorrect. I'm going to go and make sure everyone gets credit for this question. While we're in the prime factorization mood, let's carry on by talking about prime factorization of a couple of other numbers. Take a look at part 1. It says, if n equals all of these numbers all multiplied together, then what are 4 prime factors of n? And what are 10 possible factors of n? Well, the prime factors are right there, clear as day, 2, 3, 11, and 19. So if you're going to ask, what are the 4 prime factors? They're right there, 2, 3, 11, and 19. Can you find 10 possible factors of n? Well, all you have to do is kind of find ways to multiply these together in different ways. And notice you can use the number 3 5 times. You could use the number 11 twice. You could use the number 19 3 times. So there are a whole bunch of different examples of numbers you could use. Let's go through that motion, okay? So first, what are the 4 prime factors? The 4 prime factors are 2, 3, 11, and 19. For the second one, it says, now, what are 10 possible factors of n? Well, I could do 2 times, of course I have these 4, Why not list those first? Because those are also possible factors of n, right? They didn't say they want composite factors, they want factors. There's 4 of them right there. If I take these and multiply them together in different ways, I arrive at other answers, like 2 times 3 is 6, 2 times 11 is 22, 2 times 19 is 38, 3 times 11 is 33, 3 times 19 is 57. I have 9 here. I notice I can use 3 more than once because there are 5 3s in the list. So how about 3 times 3 times 3, which is 27. And now I have, 10 of them. So this is what we were looking for number 1. We're able to recognize that you can assemble composite numbers using different primes that are part of the prime factorization. In part 2, we're asking you to find the smallest number with the following factors: 2, 6, 8, 22, 30, and 45. And in this case, once again, we're looking at that other methodology we discussed in our last section, where we examine the prime factors and use them to assemble our least common multiple. The smallest number with the following factors is going to be the least common multiple. So what we could do is we could take all of those numbers and write out the prime factorizations of them like you see there. 2 is already prime, 6 is the same as 2 times 3, 8 is 2 times 2 times 2, etc. Let's put these all out, okay? 6 numbers. I have 2, which is just 2. I have 6, which is 2 times 3. I have 8, which is 2 times 2 times 2. I have 22, which is 2 times 11. Then I have 30, which ought to be 2 times 3 times 5. And of course, you would go through the work of getting these prime factorizations on your own, right, in a different way. And then we have 45, which is going to be 3 times 3 times 5. That's a 5. Okay. So if we're going to try to assemble the least common multiple, what we're going to have to do is we're going to start with this 2. We say, well, we've used a 2, let's circle it. Is there anywhere else that I've used a 2? I used a 2 in here. I used a 2 here. I used a 2 here, and I used a 2 here. So that's 1, 2. 1 and only 1, 2. Okay, let's go to the next thing, 3. I'm going to use this 3. Can I use 3 in any other number? Here and here. So there's a 3. So take a look and let's pause for a minute. Look at how many numbers are circled and look at how many numbers I've written in the prime factorization so far. As soon as I see the first 2, I circle a 2 if I can out of every other number that I'm doing. Now these 2s are to be disregarded when I'm looking at new numbers. Then I go to the next number that's not circled. This one has been circled. This is the next one, 3. So now to exercise 3, I go to every number and circle a 3 if I see it. There isn't one here. There isn't one here. There's one here, so I circled it. And there's one here, so I circled it. Next, I go to the next thing that's not circled, which is this 2. Do I see any other 2s I could circle anywhere? The answer is no. I go to this 2. Are there any other 2s I could circle anywhere? The answer again is no. Then I go to this 11. Do I see 11 anywhere that I could circle? Again, the answer is no. Here's 5. Do I see 5 anywhere else that I could circle? And the answer is yes, right here. So I write 5 one time. And there's a 3 left lingering here, so I have to put that there as well. Finally, put them in order. 2 times 2 times 2 times 3 times 5 times 11. This is the solution right here. I think I missed a 3. Yeah, I did. Look, there's 2 3s. See them? It's 3 times 3. There's one more 3 in there. All right? All right, now, doing it for number 2, you do the same situation. It's the same methodology. Let's go through doing that on number 2 now. On number 2, we're asking you to do it for 50, 126, and 490. Now, again, you've already gone through all the work of it. Let's write it in this way this time. 50 is 2 times 5 times 5. 126 is 2 times 3 times 3 times 7, and 490, 2 times 5 times 7 times 7. Okay, once again, we're going to do the same process to try to assemble what the new least common multiple ought to be. So to do that, what I'll need to do here is start with this 2. I circle the 2. Do I see 2 in any other number? Here and here. I write 2 one time. Next, I go to the 5. Do I see 5 in any other number? Not here, but here I see it. I write 5 one time. Next uncircled number is 5 again. Circle it. Do I see 5 anywhere else? No. Write 5 one more time. Now we move on to the next number. 3 is here, but I don't see 3 in the next number, so I'll put a 3. Once again, here's 3. I don't see 3 in the next number. I write it again. Now when I get to 7, do I see 7 in any other numbers? Yes, I see it right here. So because of these two, I'm writing this 1, 7. And then I have one last 7. Now it's not necessary for you to multiply this all the way up together. 2 times 5 times 5 times 3 times 3 times, that means a very, very large number. The answer to this question is most appropriately written as you see here with times in it that way. And when you take your next exam, you'll see answer choices that look like that when you're doing your studying. Okay, so I'd like to talk to you before we dismiss about one specific important question that's in WebAssign. I wanted to bring your attention to it. Let's do that now, and then we'll dismiss, my friends, okay? In WebAssign, there is this one question that I really want to share with you and talk to you about. Okay. This question is in your practice assignment associated with chapter 11, where you're going to be talking about the idea of even and odd numbers. And I want to just talk to you a little bit about how you can interpret what's supposed to be going in here. This is something that we like to call an addition table. And the way an addition table works here we have even, here we have odd, and then we have here even and odd. And notice that in the corner, we have this lovely plus sign, which tells you it's an addition table. We also have another case with a multiplication table, but it's the same situation. It might be practical for you guys to open this question up right now. It is available for you to do in WebAssign. If you want, you could open it and look at it and put the answers in with us right now as we're talking. Okay, so we're trying to ask the question, what happens when you add together an even number plus an even number? And they didn't really explain this very well at all in your chapter, so I want to talk to you about it before we dismiss. When you add an even number plus an even number, you might be able to see with your intuition that you do get an even number, right? And if you get an even number, that's because here are some examples. 14 plus 22, yeah, that's going to be even, right? 28 plus 8, that's going to be even, right? It might help you to go through a couple of little examples to confirm in your mind that every time you add two even numbers, you do certainly, in fact, get an even answer. What happens when you add an even number and an odd number? 24 plus 5, look at what you get, right? So these little cases here kind of make it pretty clear that it turns out being this way. And that has to do with when you add. When you're adding, if they're both even, the answer is even. If they're both odd, the answer is going to be even. 19 plus 5, 24. So every time you add up two odd numbers, you get an even answer. The answer solution for this question in your WebAssign practice today looks like this, with even, odd, odd, and even in this way, just as I mentioned, so that you understand that when you add two even numbers, it's an even answer. When you add two odd numbers, it's an even answer. If you add two numbers and they're different, meaning odd and even, the answer will be odd. Now, that is how it works for addition, and this is called an addition table. Let's now talk about a multiplication table. What happens when you multiply together two even numbers? 14 times 4, the answer is going to be 56. I got an even answer, right? So when you multiply together two even numbers, you get an even answer. When you multiply an even times an odd, you also get an even answer. 14 times 3, what's that going to be? 42. And that's, again, even. So an even times an odd is even. And because of our because we're comfortable with the commutative property, of course, an odd times an even also would be even. When we multiply two odd numbers, that's the only time that we wind up with an odd solution. 13 times 5 is 65. So there we go. So when you do your web assignment practice and you come to this question, let's remember this conversation we had in class where you're talking about something called an addition table. Here we're talking about something called a multiplication or times table. We're trying to answer the question, what happens when I multiply any even number times any even number? The answer is it's always an even product, and so on. So filling in these tables at the beginning of that question will help you with answering the rest of the little questions that are associated with that exercise. I just wanted to make sure, because we didn't talk very much about even and odd, except for the fact that 2n is the best way to express an even number. Okay, my friends, so we are done with our lesson for today. I'm going to go and take attendance and then we'll dismiss. And I do apologize for the little glitches with our exam. Like I said, I was kind of anticipating that there'd be some little issues, and I really want it to be very fair for our students and that they get fair grades. So right now your exam grades are not finalized. I have to go in and make some small adjustments. I'm going to do that today, and we'll talk about it again on Thursday. You should see a change in your grade by the end of the day today. When we get together on Thursday, we'll talk more about it. If you have any specific issues with your exam and you feel like you'd like to ask a question, feel free to send an email, or you could also, of course, bring it up here in class. I'm going to pause now, and I'm going to go take attendance, and then we'll come back and dismiss. Thanks a lot for your attention, everyone.